Good morning, students. Today class will go about the equations of straight lines. First of all, I have to think on how to define a straight line. What do I need to define a straight line and this straight line to be the only one? First of all, to define a straight line, I need a direction. A direction means if this is a horizontal line, this is a vertical line, or this is a line that forms any angle with the horizontal line. The direction of the straight line can be defined using a vector, because a vector, each of the vectors has a different direction. If I take a vector that is parallel to the straight line, I have the direction of the straight line defined. This vector is usually known as direction vector. Here, for example, we have an example of how a direction vector can be. This is the direction vector in this drawing, what is parallel to the red line, that is the line we are going to study. But once I give the direction, I have several lines with the same direction. To take the one I want, I have to select one of the points of the line. So, to define a straight line, I need two elements. I need a point of the straight line, and I need the direction vector. With just these two elements, I can define the equation of a straight line. But how to define this equation? In fact, I'm not going to define just one type of equation. I'm going to define several types. First of them, the vectorial equation. Okay, using these two elements, the points and the parallel vector to the straight line, I can define the equation of a straight line. How? I take any point of the straight line, x of unknown coordinates x and y. This x and y that has no numbers means that I don't know the real value of x and y. It depends on the value of x, the value of y I have to take. This represents any of the infinite amount of points that the straight line have. So, if x is this general point of the straight line, the vector px, this vector, must be parallel to the direction vector because it belongs to the straight line. How can I write the condition of being parallel? Being parallel means that one of the vectors must be a number, unknown number, this is a parameter, multiplied by the other vector. But again, as I know the coordinates x, y, I don't know the value of any of them, but I know them. I can use them as known to construct the vectors. I can calculate the coordinates of vector px using the coordinates of the final point minus the coordinates of the initial point. Remember that even when I can subtract the coordinates, because the coordinates are numbers, I cannot subtract the points because I haven't defined an operation with points. To subtract the coordinates and write it mathematically right, I have to substitute the coordinates of the point by the position vector that has the same coordinates, and vectors I can't subtract. So the coordinates of the final point can be written as the coordinate of the position vector of x minus the coordinate of the position vector of p. So position vector for x minus position vector for p must be lambda multiplied by the vector, the direction vector I already defined. And if I take this vector that here is subtracting and send to the other side adding, I arrive to this result. In fact, this is the vectorial equation. But I don't like usually written this type of things just with vectors. I like using the coordinates. The coordinates of the position vector for x are the coordinates of point x, xy. The coordinates of position vector for point P are the coordinates for vector P. Lambda is lambda, just a parameter, and the coordinates of vector V I defined in the previous slide as V1, V2. And this is the vectorial equation. How can I calculate this way the different points of the straight line? Each time I give to lambda the different values, I can obtain the different point of the straight line. For example, if I give lambda the value 0, I have 1 point. If I give lambda the value 2, I have another point. If I give lambda the value 59, I arrive to a different point. And so on, I can calculate all the coordinates of all the points of the straight line. When I write the vectorial equation, finally, I just have x, y equal coordinates of the point plus lambda multiplied by coordinate of the vector. And lambda is the parameter. Now I'm going to define another type of equation for the same straight line. I'm going to take at the beginning the vectorial equation as I defined in the previous slide. Here I have a product of a number by a vector. It means multiplying this number into the vector in both coordinates, as I did here. Once I did that, I can do this operation. I can add these two vectors. As I know, I have to add the first coordinate with the first coordinate, the second coordinate with the second coordinate, arriving to this result. What does it mean? It means I have here an equality between two different vectors, and when I have this situation, I know the first coordinate of the first vector must equal the first coordinate of the second vector, and the second coordinate of the first vector must equal the second coordinate of the second vector. Finally, I have split this vectorial equation into two numerical equations, and these two expressions are called parametric equations. When I have the parametric equations, again, I have the same structure, but split it into two equations. So, this is the generic point. First of all, I have the point I know, the parameter, and multiplying the parameter, I have the vector, the parallel vector, the direction vector I told you. Okay, so I don't need to start writing the vectorial equation to obtain the parametric equation. I can obtain them directly. I'm going to speak now about the continuous equation. I start by the parametric equation. What happened? As I told you, parametric equations in fact are another way of writing the vectorial equation. It's just to split a vectorial equation into two numerical equations. But probably you don't like this way of giving values to the lambda, to the parameter, and obtaining different points. You would like to do as we usually do when I have an equation for a straight line, as you had when you have linear functions last year, and you have to represent them. You gave values to the x and calculate the value of y corresponding to each of them. But how can I do that? I don't like to have a parameter. So why can I make this parameter disappear? The easiest way is taking the first equation and calculating the parameter here. This x1 here is adding. I can send to the other side subtracting. And I have x minus x1. Sorry for the letter, but it's not easy to write with the mouse. Equal lambda multiplied by v1. So this v1 here is multiplying. I can send to the other side dividing, and I arrive here. If I do the same with the second equation, I send y1 to the other side subtracting, and I have y minus y1 equal lambda multiplied by v2. So sending this v2 to the other side dividing, I have lambda equal y minus y1 divided by v2. So finally, as I have two values for the parameter lambda, and these two values must be equal because in fact they are the same parameter, I can equalize both expressions and I arrive to this equation that is called continuous equation. In this equation, again, I have very clear the structure as x minus the point, the coordinate, the x coordinate in the numerator. In the other side, I have y minus y1, okay? And in the denominator, I have the coordinates of the vector. So if I have a straight line written in the continuous way, I can subtract values of points and vectors. And if I have point and vector, I can write directly continuous equation without needing to write vectorial equation and parametric equation, even when I can do it. Now I continue with point-slope equation. To construct point-slope equation, I start by the previous one with the continuous equation I already present in the previous slide. This v2 here is dividing. I'm going to send to the other side. And in the other side, it's going to be multiplying this numerator. So I can write this way. Y minus y1 equal v2 multiplied by x minus x1 all divided by v1. But it's the same, dividing everything, making this longer, or dividing just v2. I prefer writing this way. Why? Because v1 divided by v2 will be a couple of numbers divided. But in fact, in this equation, as it's written, it doesn't matter the value of v2 and the value of v1 individually. The only thing that has an importance is the quotient between both of them. And this quotient I'm going to define as m. M, I forgot to write in the slide. M is going to be called slope. And once I have the direction vector, I can calculate the slope as the y coordinate of the vector divided by the x coordinate of the vector. So finally, substituting this quotient by m, I arrive to the point-slope equation. Y minus y1. Here I have point again, and m, what is called slope, represent in fact the vector. Okay? And finally, the last equation you are going to need to know. Slope-intercept equation. Again, as I have been doing in the previous slide, I start with the point-slope equation. What happened? Here I have a bracket. I can multiply this bracket. M multiplied x and m multiplied x1. And this y1 here is subtracting. I can send to the other side adding. I place here, but I don't mind placing here or here. This way I group because x is an unknown quantity, x1 is a number, m is a number, x1 is a number. So this way I separate where the unknowns are from where the numbers are. Again, as it happened in the previous slide, I have here this quantity, m1 minus m multiplied by x1. This is just a number, and I don't know to separate the different values, and I can define n as y1 minus x m multiplied by x1. This n is called intercept. Sorry, because I forgot to write in the slide, sorry. So when I substitute all this quantity by n, I arrive to the slope-intercept equation, y equal mx plus n, what is probably the type of linear equation you already know. In next exercises, we will know how to write directly this equation very fast. For the moment, I just prepared an example of how to use this equation, how to calculate the different equations, just knowing the point and the parallel vector. I'm going to calculate the equation of the straight line passing through the point 3 minus 2, and that is parallel to the vector 1, 6. First of all, I'm going to write the vectorial equation. As I told you, this is very easy. I just have to write x, y equal coordinates of the point 3 minus 2 plus lambda is lambda, multiplied by the vector 1, 6. This is the vectorial equation. Enough. I've ended. But if I want to calculate the others, I have to continue with the process. How? This lambda I multiply into the vector, and I have x, y equal 3 minus 2 multiply plus lambda 6 lambda. And I have now to add these two vectors, and I arrive to xy equal 3 plus lambda minus 2 plus 6 lambda. When I split this equation into two different equations, one for the first coordinate, one for the second coordinate, I arrive to the parametric equation. X must equal 3 plus lambda, y must equal minus 2 plus 6 lambda. Enough if I just want to calculate the parametric equations. But if I want to continue calculating the other equations, I have to calculate lambda in both equations. In the first equation, these 3 here is adding, I send to the other side subtracting. This minus 2 here is subtracting, I send to the other side adding. So y plus 2 equal 6 lambda. And this 6 that here is multiplying, I send to the other side dividing, and I arrive to lambda equal y plus 2 divided by 6. As I have these two expressions for lambda and both of them must be equal, I arrive to the continuum equation equalizing both of them. When I don't have a denominator in the continuous equation, remember that I have here a 1. So without watching at the upper part of the exercise, I know that the point is what I'm subtracting to x and y, so 3 minus 2, and the vector is 1, 6. Okay? If I take this 6 and I send to the other side, multiplying, I arrive to the point slope equation. Y plus 2 equal 6 multiplied by x minus 3. And finally, I arrive here, I end here if I want the point slope equation. But if I want to arrive to the last type of equation, I start by multiplying this bracket, y plus 2 equal 6x minus 18. And these two that here is adding, I send to the other side subtracting, and y equal 6x minus 18 minus 2. So finally, I arrive to the slope-intercept equation, y equal 6x minus 20. And that's all. Now you have to practice and do the exercises I tell you.